Yeah, right. So thank you very much. Yeah, so let me begin by thanking the organizers for actually this kind invitation to speak. Okay, so I'm going to talk about some aspects of celestial amplitudes and actually graviton scattering amplitudes. Okay, so let me begin with a brief review so as to set the stage. Why is this? Yeah, nice. So we learned yesterday from actually Stefan Steinberger's very nice review talk. Is that the Lorentz group in four-dimensional Minkowski spacetime acts on the celestial sphere at null infinity as 2D conformal transformations. Now there is a way of writing S matrix elements of particles in a basis which makes this conformal transformation property actually completely manifest, which has been worked out in this set of papers. And for massless particles, as also Stefan reviewed in his talk, is that there is that this basis change is particularly simple and is implemented by an integral transform, which is known as the Melli transform. And that gives us, and the relation is shown in this equation below here. So on the right-hand side, we have an endpoint scattering amplitude, which is characterized by the energies of the particles involved, which are denoted by these omega i's. The sigma i's, they correspond to the helicities of the massless particles. The zi's and the zi bars, so they should be thought of as the coordinates on the two-dimensional celestial sphere at null infinity. And this dependence of the amplitude on this z and z bar coordinates actually comes to this parametrization of null momentas, which is written here. And on the left hand, then we do an integral transform where we integrate with respect to the particle energies with a particular measure. And on the left hand side, what we get is an object which by construction is manifestly transforms as in the same way as an endpoint function in a 2D CFT does. Okay. So in this case, these deltas, which appeared in the subscripts here of these operators, should be thought of as their conformal dimensions, and these take the values 1 plus I lambda, with lambda being a real number, and the sigmas, which were the helicities of the massless particles on the right hand side, they become the spins. And for these local primary operators. Now, this way of thinking about scattering amplitudes also provides a very nice setup for understanding or developing some notion of holography for quantum theories of gravity in asymptotically flat spacetimes. So what we would like to do is that we would like to understand the properties of this putatively dual celestial CFT a bit better. Now, in that regard, one of the things that we should try to understand, at least at the least, is the structure of the operator product expansion. Now, the OP is a fundamental aspect of any CFT, and if we claim to understand the celestial CFTs, then in that case, we should better understand the structure of the OP in these CFTs. So now you can ask that what feature of scattering amplitudes might correspond to the OP in this in the dual CFT, and the answer to that question is the following: is that the celestial OP can be extracted by studying the collinear limits of scattering amplitudes. So one way of seeing that is as follows. So let's consider in a typical Feynman diagram, consider the situation where, let's say, two particles are with momentas P1 and P2 are becoming collinear to each other. Then if these are massless particles, then from the effect, then from a 3-point vertex, the contribution to the propagator, or basically the contribution to the internal propagator, will be of this form, which is 1 by 2 P1 dot P2. And if I rewrite these momentas in terms of this Z and Z bar parametrization, then you can see that this P1 dot P2 translates into a quantity which looks like Z1 minus Z2. So therefore, in the limit where P1 becomes parallel to P2, this factor diverges, the P1 dot P2 diverges, and correspondingly there is a singularity as we take Z1 close to Z2. Okay, so in that sense, the collinear singularities of scattering amplitudes can be mapped to the leading OPE type singularities in the dual CFT. Now we expect asymptotic symmetries of asymptotically flat spacetimes to impose powerful constraints on the structure of this OPE. In fact, in this very nice paper from last year by Monica Pate, A. Emre Clariu, Strominger, and E1, what was shown is that one can use the global symmetries associated to subleading soft gluon and sub-subleading soft Graviton theorems and combine them with the global space-time translation symmetries and completely fix the structure and of the leading OP and completely fix the leading OP coefficients of gluons and gravitons. Okay, and there are also some papers where the constraints from Poincare symmetries for massless as well as massive particles has also been studied. Okay, so in this talk, the main question which I want to address is that what is the structure of the higher order terms in the celestial OP? So we saw that the leading term in the celestial OPE is basically so that basically corresponds to actually just the leading singular terms in the okay. So the leading singularity in the celestial OP just corresponds to actually the collinear limit in the scattering amplitudes. But what happens to the higher order terms? So in standard 2D CFTs, there is a very nice way of answering this question, because we know that the OPE can be organized into representations of the underlying Virasoro symmetry algebra. Right. So now what we want to see is that whether a similar structure exists for the celestial CFTs as well. So I will answer this. So I will try to answer this question in a sort of limited setting, and that will be as follows. So I will consider the case of tree-level MHV Graviton amplitudes, which are in a sense the simplest, gravity amplitudes that one can consider, and then take the OP in the corresponding dual celestial CFT. What I will show is that the OP in that case can be organized into representations of an infinite dimensional local symmetry algebra, which will not quite be the Virasoro symmetry algebra, but this symmetry algebra will comprise of a certain current algebra that I will construct using the subleading soft Graviton theorem, and it will also involve supertranslations. So here's an outline for the rest of my talk. So first I will discuss what this current algebra is, which I just advertised. And then we will see how this current algebra plays a part in the discussion of the celestial OP of gravitons. Okay, so I should also say that you should feel free to stop me with questions.
Hi, Sudip. I had a question actually. So in the usual conformal field theories, OPE gives a convergent expansion.
Yeah.
You know, that's why.
Yeah. Right.
But like in ordinary quantum field theories, of course, we can do OPE, but that is not a convergent expansion. So now, since the celestial amplitudes are like a change of basis of the usual QFTs, I mean, these OPs will also not be convergent. We don't expect them to.
Yeah, so potentially, but at this point of time, I won't have anything better to say about it. We cannot, because a priori we don't know whether these CFTs are actually bona fide local conformal field theories. So yeah, but at least one thing which we can say is that from the explicit computations which one can do by taking explicit examples of scattering amplitudes, so in that case one can actually try to extract the OP from there, and in that case, and it seems that the OP actually does exist, but whether it is actually truly a convergent expansion or not, so that actually remains to be investigated.
Okay, thanks.
Sorry, I'd like to expand a little bit on that question. So for the examples where we have the amplitude, do we actually have the OPE representation? I mean, the OPE expansion of that amplitude? Do we actually have, like, rewriting the, for example, rewriting the MHV amplitude as a sum over conformal blocks with particular OPE coefficients? Do we actually have this in the literature, or?
Yeah, so basically in this talk, what I'm going to show is that in this talk, I won't be showing that is that, let's say you, okay, so say suppose you give me, say suppose the 4-point MHV amplitude. Right. And what I won't show is that can be organized or expanded into some conformal blocks. But what I will show is that there is a sense in which there is an OPE expansion, in the sense that you can bring two operators in that 4-point function close to each other, and you can expand that into a sum of other operators. And that structure is precisely the structure of an OPE.
Okay, maybe just one quick follow-up question. So sure. Since we're really only so we're one of the things about mapping to the celestial sphere is that you're mapping the Lorentz invariance to the conformal. And so that suggests that we're supposed to, if I wanted to do an expansion, I would do it on the global conformal blocks. Right. So because the fact that you say that now there's some kind of Virasoro symmetry that is underlying, is it that you're saying that actually that the preferred expansion is the Virasoro blocks instead of the global blocks?
So in this case, I would say that the preferred expansion blocks will not be just Virasoro, because in this case we have more symmetries, right? And the celestial conformal field theory also has super translations. So I don't know what exactly the block expansion will be, but whatever that expansion is, that should involve also the super translations, so it should be so it should be more than just actually the conformal blocks.
Okay, thank you.
Okay, thanks.
Sorry, can I ask just one more question? So this is your second last point, that you're looking at the tree-level MHV amplitudes.
Yeah.
But if you take two operators and just bring them close to each other and they do an OP expansion, and the other operators in a correlation function can have arbitrary helicities, right? So how does it, once you have an OP expansion, how does it matter which MHV or other, I mean, the OP expansion to the order you are carrying out will not change, right?
Yeah, so that is right. So you are basically saying that the OPE, if it exists, should be an operator statement. But in this talk, I want to also show that the OPE can be organized in a particular way. So the statement will be that the OPE can be organized in terms of representations of a certain infinite dimensional symmetry algebra, and that symmetry algebra will exist only for the case of MHV amplitudes.
I see. Okay, thanks. Thank you.
Okay, thanks. Okay. So now let me begin with a discussion of the conformal soft theorems and associated current algebras. Okay. So to this audience, it is really pointless to emphasize emphasize what important role is played by soft theorems in the study of scattering amplitudes. But in this talk, I will be particularly interested in the soft limits of gravitational scattering amplitudes. Okay. So at tree level, we know that gravity amplitudes obey soft factorization relations of the following form, where on the left-hand side, I have an n+1 point scattering amplitude with a graviton insertion, whose momentum is being taken to be soft, that is denoted by Q here. And on the right-hand side, I have a factorization in terms of an n-point amplitude without the soft graviton. And then there are certain prefactors which are organized in powers of the soft momentum. So for example, at leading order in the soft momentum, we have what is known as the Weinberg or the leading soft factor. Then we have the subleading soft factor, sub-subleading soft factors, and so on. Now, what I want to do is that we want to understand the version of this on the celestial sphere. But now we see that the notion of an energetically soft particle is not immediately apparent in the conformal basis, because in order to construct the celestial amplitude, we had to integrate over the energies of all particles involved from 0 to infinity. But in this case, what has been understood in recently that the role of the soft momentum is now substituted by the following notion, where we send the conformal dimensions of one of the operator insertions to actually some integer values. So for example, if we take the conformal dimension to 1, then that is what is referred to as the leading conformal soft limit. Delta goes to 0 is known as the sub-leading conformal soft limit, and so on. And it can be shown that there is a correspondence between these soft limits where delta goes to 1, 0, and -1, and actually the corresponding soft limits in the usual momentum space. So first let me actually talk about the subleading conformal soft limit, because this current algebra which I advertised is going to be constructed out of that. So for this, let me consider an n+1 point correlation function on the celestial sphere of the following form, where the first insertion is basically an operator corresponding to a graviton. So I will and I will take the spin of this operator to be +2. And I will refer to this as the positive helicity graviton primary operator. And then the rest of the insertions, which are denoted by phi hi bar, within this case will be some generic matter conformal primaries, in the sense. Okay, so some of this could be gravitons, but at least for now, we don't care what these other insertions are. And I have changed my notation from the earlier slide a bit, in that I have explicitly introduced the left and right conformal weights, which are these h and hi bars, and they are related to the dimension and the spin in the usual way as shown on the right here. So now the statement of the subleading conformal soft limit is basically the following, that if we multiply this correlation function with, let's say, delta, and then take the limit where delta goes to 0, then the n+1 point correlation function factorizes, and it factorizes in the following fashion, which is the last equation here, so we have the n point correlation function on the right hand side, and that is multiplied by a certain set of factors, and I will call this prefactor the subleading conformal soft factor. So now what I'm so now let's make a couple of observations here, which is that if we look at this soft factor in this equation here, then we see that the subleading soft factor actually depends at most quadratically on the z bars, okay, where z bar was the anti-holomorphic actually coordinate for the insertion of the soft graviton operator. So what I can do is that I can expand in powers of z bar, and then naturally I will get 3 sets of terms. So for this, I should also say that I will be treating z and z bar as actually independent variables, which can be done if we take the bulk spacetime to have actually split signature metric. And so we do that. We treat z and z bar as independent variables, and then we expand the soft factor in powers of z bar. So we get 3 sets of terms. We get one term which does not have any whose prefactor is order 1. Then we get another term whose prefactor is order z bar, and then another term whose prefactor is order z bar square. So now these objects J1, which I have called J1, J0, and J-1, should be thought of as currents. And the correlation functions of these currents with other primary operators, they take the following form. So for example, the correlator of J1Z with other primary operators is basically given by this, where we have L1 bar divided by Z minus ZK and acting on the endpoint correlation function. So here we should think of the subleading soft operator, which is this S1 plus here, as the generating function of these three sets of currents. Okay. So now we can go ahead and consider the modes of these currents, J1, J0, and J minus 1. The modes can be defined in the standard fashion, and we can also compute their commutation relations. Okay. So the commutation relations, they take the following form, where the JAM and JBN commutator is equal to A minus B, J of A plus B, and M plus N. So here so let me explain the notation a bit. So the superscripts A and B, they denote which current I'm talking about, whether I'm talking about J1, J0, or J minus 1. And then the subscripts denote the modes of the individual currents. The modes, since these are modes, these run over all integer values. Now, so now if you look at this commutation relation, we immediately see that this commutation relation is nothing but the commutation relations for a level 0 current algebra. And I will call this current algebra an SL to C bar current algebra. So in this case, why this terminology SL, why this terminology SL to C bar? So that is actually fairly easy to motivate. Because if you look at the zero modes of these currents, which are defined by J1, 0, J0, 0, J and J minus 1, 0, that is nothing but L1 bar, L0 bar, and L bar minus 1. Now these are basically the generators of the anti-holomorphic Lorentz transformations, right? And so therefore we will call this current algebra an SL2C bar current algebra. So now it is also important to note what the commutation relations of these modes of the currents are with other actually primary operators, and that is given by these commutation relations. So these are easy to compute once the commutation relations with L1 bar, L0 bar, and L bar minus 1 are given, which are also known, and they take the standard form. So now in this current algebra, what we see is that the holomorphic conformal transformations are missing, which are the SL2C conformal transformations, which are generated by L1, L0, and L minus 1. So that does not feature into the current algebra yet. So then we have to, so then we should mention what the commutators of the global SL2C generators with this current algebra is. And that can be also computed, and it takes the following form, where Lm Jan is equal to minus of minus n times J A m plus n. Okay. Okay.
Sorry, Sudip. So if you had not worked with the split signature, just with the Minkowski spacetime, then you should get just one SL2C current algebra, right? Yeah, you are getting two, I guess, holomorphic and anti-holomorphic.
Yeah, yeah.
But you could do without going to split. Is that okay? I mean,
so we could do without split signature because at the end of the day, when we finally compute the OP coefficients, the fact that at the end of the day, the OP coefficients and all, they will not depend on whether we went to split signature or not. But going to split signature is just in this case a convenient choice.
Okay.
Yeah, and since we can always actually analytically continue scattering amplitudes as is usual in our business.
Okay.
Okay, thanks for the question. Okay, so now let me make a few comments on the interpretation of this current algebra as in terms of diffeomorphisms. So what we can do is that, let's say we consider a class of infinitesimal diffeomorphisms of the following form, where let's say Z goes to Z and Z bar goes to this where Z bar plus this combination AZ, BZ plus CZ, where A, B, and C are actually analytic functions of Z. Now what we can do is that we can mode expand these functions and define a basis of vector fields, which I have denoted by Jn minus 1, J0n, and J1n, and these take the form, and these are given by these differential operators. And we can compute the commutators of these differential operators. And it's not a surprise that the commutation relations are again those of a level 0 SL2C bar current algebra. So what we learned from this is that the current algebra that we mentioned before can be geometrically interpreted as the subalgebra of the algebra of diffeomorphisms on the plane with analytic singularities. And one usefulness of this interpretation is that this might be useful in thinking about this current algebra symmetry in terms of the asymptotic symmetries of asymptotically flat Minkowski spacetimes.
I have a quick question. Sorry. So
Yes.
I'm just wondering. So we know that the 4-point celestial sphere amplitude, because of array invariance, actually lies on a line.
Exactly. Yeah.
And so what does that mean in terms of if I'm looking at the 4-point OPE? Would these become degenerate or somehow like because it's on a line?
Yeah. So that so that is right. So in this case, basically, what you're referring to is that if I compute the 4-point function, then I have the cross ratios, let's say, and then because of translational invariance, the cross ratios are said to be real, right? So actually, z becomes equal to z bar in that case if I denote z and z bars as the cross ratios. So that immediately does not actually is not a problem. But what I will show in the later half of the talk is that if you, let's say, start from the 4-point amplitude, the 4-point celestial amplitude, and then try to do the OP between two operators, then by doing that you will get some 3-point, then that will factorize into some 3-point actually celestial correlator, right? But as will turn out is that that 3-point function has some limitations in the sense that some of these current algebra generators will have a trivial action on that 3-point function, and so what we will do instead is that we will actually start with higher point functions, and we'll try to construct the OP from there. So and that is just to actually manifestly see the action of all the non-trivial current algebra generators in the OP.
Okay, thank you.
Okay.
So Sudip, in the first equations, are in the ABC are meromorphic, right? Here they are not. Okay, so they can have singularities in the.
Right. Okay. So now our eventual goal is to study the OP of graviton primaries on the celestial sphere. But in order to do that, it is first useful to consider the OP of the subleading soft graviton operator, which was being denoted by S1 plus in the previous slides, and some other generic actually matter conformal primary. Okay. And that will place an important constraint in the sense that if we take this other so if we take this other matter primary to also to be a graviton, then that should then the result which we get should agree with what we have from the general statement of the subleading conformal soft theorem. Okay. So in this case, what we want to do is the following. So again, we start from the subleading conformal soft theorem, which is the statement that we have this n plus 1 point correlation function, and that factorizes into an n point function. So in this n plus 1 point correlation function, let me take the insertions of the subleading soft graviton operator, which is denoted by S1 plus, and some other matter primary, let's say this phi h1 bar. So let me take the insertions of these two operators to be close to each other. And that would amount to taking an OP between these two objects. So then what I should do is that I should now expand the right hand side in powers of z minus z1 and z bar minus z bar o, and then that allows me to extract the OP. So one can carry out this analysis, and it turns out that the OP takes the following form, which is shown in this boxed equation here. So now in this equation, let's try to understand what is. So now let's try to understand what the various terms are. So the first observation is that we see in this OP that we have terms which are singular as well as regular with respect to z minus z1. Okay. So the interpretation of the regular terms is actually easy to understand, because these regular terms, which are denoted by whose coefficients are of the following form: ja minus p phi hh bar zz bar with p greater than equal to 1. These are nothing but the current algebra descendants of the primary operator phi hh bar. Okay. And the correlation functions of these descendant operators with other primaries, they can also be computed in the standard fashion, and they take a form which is also familiar from ordinary 2D CFTs, in the sense that the correlation function of descendants with other primaries can be expressed fully in terms of the correlation function of the remaining primary operators, but now with some differential operators acting on the correlation function of the primaries. Okay. So for example, if I take J1 minus P phi H1 bar, stick it inside another correlator with n minus 2 insertions of primaries, then I get some correlator of the primary correlation. So then I get the endpoint correlation function of the phi's, and with a particular differential operator acting on it. And the structure of these differential operators, they can also be easily worked out from starting with the subleading soft graviton factor. Okay, so now let's make.
Sorry, in the first equation you just explained, the right hand side, is it in the right hand side the product is I equal to 2 to n? I got a bit confused in the.
No, so in this case, the product on the right hand side is
the second line, the next line.
Yeah, so basically in this case, the product should be from 1 to n only, because as you know, is that if I take an okay, so this is exactly similar as what happens in 2D CFTs, right? If I take an endpoint, okay, so let's say I take an endpoint correlation function
Yes.
where so I take an endpoint correlation function where I take the descendant of one of the operators. Then the resulting correlation function is just the correlation function of all the primaries involved in the original correlator. But now there is a differential operator which acts on this endpoint correlation function.
Okay. I see. K is not 1, so it doesn't. K is not.
Yeah, right. So K is not 1. Yeah, right. So in this case, that's important that we include. So that's important that we exclude the K equal to 1. Okay, so now let's make a couple of other observations which are apparent from this OP. So from the OP of the subleading soft graviton and the generic matter primary, we can also infer the following two statements. So we see that if we act with the modes of these currents, where where the mode number n is actually positive, in that case we see from this OP in this boxed equation is that if the mode number is positive, then all those terms, so then all those modes should annihilate the primary operator, right? And also if we consider, let's say, the particular current J1 and its zero mode, then by definition, okay, so then by definition, J1 is nothing but J10 is nothing but L1 bar, and L1 bar is basically the generator of anti-holomorphic special conformal transformations, which by definition again actually annihilates a conformal primary operator, right? So we learn these two. So these are two immediate consequences of the OP of the soft graviton operator with a generic matter primary. And so what we learn from this analysis is that the conformal primaries are also primaries of the SL2C bar current algebra. Okay, so now let me so now having discussed the subleading conformals of theorem, let me take a step back and discuss the leading conformals of theorem. Okay. So the leading conformal soft right. But before that, but before that, let me mention that we all know that the leading soft graviton theorem can be interpreted as word identities corresponding to supertranslations. Now, again, as we did in the case of the subleading soft graviton, we want to understand this soft theorem in the conformal basis. Okay. Now, since this involves the action of supertranslations, it will be useful for our purposes to introduce into the game the action of the retarded time coordinates as well, which is not usually done in the standard discussion of the conformal basis. So now, if we include the retarded time coordinates, then we have to slightly modify the prescription of the Melli transform, and that is given in this equation below, where on the left hand side we now have this bunch of matter primary operators, which also now explicitly include the retarded time coordinates. And on the right hand side, the Melli transform is almost the same as in the by now standard case. But the only difference is that there are these exponential factors which have been inserted, which are this e to the power minus I, epsilon I, omega I, ui's. These epsilon i's are just some numbers which take values in plus minus 1, depending on whether the corresponding particles in the S matrix are outgoing or incoming. And the properties of this modified Melli transform, as I will call it, has been studied in these sets of papers. So now let's take the conformal soft limit, the leading conformal soft limit. For that, what we do is the following. We take an n+1 point correlation function where we have a graviton primary operator denoted by G plus delta and some other primary operators phi hi bars. We multiply this with delta minus 1 and take the limit, and then take the limit delta goes to 1. And in that case also the correlation function can be shown to factorize in a particular way. As is shown in the last equation here. Okay, so now here we see that sorry, there was a question.
Yeah, with the modified version of this Melli transform, the difference is this exponential that appears in the Melli transform. So is that coming, like, how is that coming? Can you give a sort of a heuristic?
So that actually so in this case it is actually very easy to understand the origin of these terms. Okay, so basically this so what is being done here is that if you consider the usual conformal primary wave functions, then what you can do is that you can also consider time translated versions of those, right? You can just act with e to the power minus IHU, where H is, let's say, the Hamiltonian. So you can consider the time translated versions of the usual conformal wave packets, and this exponential factor and this exponential factor basically comes from.
I see. And like just a different question, but when you're getting the soft limit, did you say, I joined a bit late, so did you say that you're taking one of the external guys to be positive helicity? Is that an important thing in the analysis?
So actually thank you for pointing that out. So in this case what I will be doing is that the particle or the operator whose conformal dimensions I'm taking to specific integer values as we should define the soft limit. So for that I am choosing the helicity or the spin of that operator to be a particular one, and for this analysis I will take the spin to be +2 or corresponding to the helicity to be +2. So in this case the same actually analogous statements also hold if you consider the minus helicity graviton, but just for simplicity I will restrict to the positive helicity.
Okay, thank you.
Okay.
Hi Sudip, so this leading conformal soft theorem also you can write in the original basis, right? Like I think Steiberger and Taylor they write without the U.
So that also so actually that also can be done easily. So in the right, so that also can be easily done.
But there is some advantage of this. There's some
right. So in that case, the only change in these formulas will be the following: is that instead, so in that case, we won't have this explicit derivatives with respect to the u coordinates in the soft factor. But what we have to do is that in that case, we'll have to shift the left and right conformal weights of these primary operators by factors of half. And what these u derivatives basically or the purpose in life of this of these u derivatives is to basically shift the left and right conformal weights by factors of half.
Okay. So, but you will use this one for the super conformal soft, leading conformal soft.
So for my purposes, this will be actually much more useful to actually use. Right. Okay. So now, as in the case of the subleading soft graviton analysis, so let me also try to define a set of currents starting from the leading soft graviton operator, which I will denote as S0 plus. So notice that in the last equation in this slide, the soft factor depends at most linearly on z bar. Z bar appears on the numerator. So I can just expand, I can just break it up into a sum of two parts and define two sets of currents, which I will denote here as P0 and P minus 1. Okay. And the correlation functions of this P0 and P minus 1 can also be actually just simply read out from the subleading So in this case, the correlation functions of this P0 and P minus 1 can also be easily derived starting from the factors, starting from the leading conformal soft factorization measure. So this P0 and P minus 1s have also an interpretation in terms of word identities. These basically generate the word identities for infinitesimal global space-time translations of the following form, where u goes to u plus epsilon z bar and u goes to u plus epsilon, where epsilon is some small constant. So in this case, I should mention that the advantage of using the u coordinate is that it basically makes the action of the super translations completely manifest. And we also get this nice geometric picture. Okay, great. So we can now go ahead and also define the modes of the super translation currents, which are being denoted by Pn0 and Pn minus 1. Now translations commute, so the commutation relation is trivial in this case. Note that the four space-time translation generators are also part of this, and these are generated by this subset of generators: P minus 1 minus 1, P0 minus 1, P minus 1 0, and P0 comma 0. We can also consider the commutators of this mode of the super translation modes with other primary operators, and that is given by these sets of commutators. So the last point here is basically what I said in response to the question from some time back, which is that what happens when we don't have the u coordinates? We just shift the dimensions by factors of half. Okay, so we can also now consider the OP between the leading soft graviton operator and a generic matter primary, as was done in the case of the subleading soft graviton operator. And the derivation actually proceeds in exactly the same fashion. And the OP turns out to be of the following form, which is shown in this boxed equation here. And similarly, we can immediately see from this OP that if I have the following set of modes, Pn comma 0, where n is, let's say, greater than equal to minus 1, then these modes annihilate any conformal primary, phi h bar. Similarly, the modes Pn comma minus 1 with n greater than equal to 0, they also annihilate the conformal primary operators. And the modes where the generators where the modes take negative, where these modes are as follows, where let's say a is greater than equal to 2, And if we consider modes of the following form, which are, let's say, p minus a comma 0 and p minus a comma okay, I'm sorry, this should be actually -1, p minus a minus 1. This is a typo, sorry. Yeah, but the point is that if we consider these modes, then this can be thought of as supertranslation descendants, and the correlation functions of these descendants with other primary operators again can be computed in the standard fashion, and they have particular forms which are given here. Okay, so now let's try to connect the discussion of the current algebra constructed from the positive helicity soft graviton operator and the super translations. So in this case, what we can do is that we can go ahead and compute the commutators between this current algebra generators and the super translation generators. And what we find is that these current algebra generators and the super translations form a completely closed algebra. Actually, yeah, so they form a completely closed algebra. And in particular, the global space-time translations, which are generated by this set of four generators, is also included within this current algebra, which you can, or this extend, which is included within this extended algebra comprised of the current algebra and the super translations. And this can be easily seen by taking actually various commutation relations. So now in the rest of my talk, we will see how this extended algebra, and by once again, let me emphasize what extended means. So extended here would mean, extended here means the current algebra plus super translations that we just considered. And we will see how this extended algebra features in the discussion in the celestial OP of gravitons.
Sudip, hi, sorry, can I ask? So if your u goes to u plus epsilon, which is an arbitrary function of z bar, smooth, then this p will be like pnm. Is it like, I mean, even the second entry will have,
right.
That's the only difference that will happen if you had totally smooth functions on the sphere. That
exactly right.
Okay.
That's true.
So the fact that second entry is -1 and 0 is just tied to the fact that your it's only getting translated by either z bar or constant, right? Linear in z bar or constant.
Yeah.
Okay, thank you. So it can be generalized to completely arbitrary super translation. This entire construction.
Yeah, so this can be completely generalized.
Okay.
Yeah, so that is right. And also, so a posteriori, another reason why we just have this, because so in this turns out that if we take this set of generators, then that form this set of super translation generators, then they form a closed algebra with this current algebra generators.
You're saying that if you had other arbitrary super translations, then it may not form a closed. It may not form a closed algebra. If your second entry is greater than 0 in the super translation generator.
Yeah.
I see. Thank
you. Okay. Right. Okay. So in the rest of this talk, I'm going to show how all this discussion ties into the explicit construction of celestial OPs. Okay, so here is just a quick summary of what we have done so far. So we constructed an SL2C bar current algebra from the subleading conformal soft graviton theorem, which we constructed these currents and JAs and their modes, and these have particular commutation relations, and we also noted that they form a closed algebra with a certain subset of super translation generators. And the only thing which I did not specify before was the commutation relation of these super translations with the holomorphic Lorentz transformations, but that also is actually also mentioned here in the last equation. Okay, and let's also remind ourselves and let's also summarize what the definition of a primary operator is under this extended symmetry algebra, and that goes as follows. So the JANs with n positive, they annihilate primary states. L1 bar annihilates it by definition. L1 also annihilates it by definition. Pn comma 0 annihilates it for any n greater than equal to -1, and Pn comma -1 also annihilates it. And if we act with L0 and L0 bar, then that just gives the left and the right actually scaling dimensions of these operators. Okay, so let me stop here for a bit to actually see. Yeah, so in this case, before going on to the next section, let me stop to see whether there are any questions. Okay, so if there are no further questions, then actually let me proceed with this. So now we want to consider the OP from MHV scattering amplitudes. So the celestial OP of for two positive helicity graviton primary operators was studied using the modified version of the Melli transform, which I showed before. For the case
can
of,
ask, sorry, can I ask?
Sure.
From the perspective of the soft theorem, this just look at this super translations which are of this type, you know, the either some AZ plus BZ Z bar type.
Right.
So from the perspective of soft theorem, they look like a strong restriction, right? Because soft theorem imply, I think, that you can have any function of Z bar super translation, like any real function in the Minkowski signature. So you can go to U plus some F of Z bar, where F is arbitrary function. So like from that perspective, this choice of your function looks
so actually that so I think actually that you could do. So for example, here I started with the leading conformal. I started with the soft theorem for the positive helicity soft graviton, right?
Yes.
But what you could do is that you could start with the negative helicity soft graviton, and then in that case you will actually have this structure which you are referring to actually.
Okay. Okay.
So so basically in this case I am getting I'm restricting to this set of super translation modes because that is what you get actually from the positive helicity that is what you get from positive helicity leading soft graviton factor. Okay, right. So as I was saying, that the celestial OP of for the case of positive helicity gravitons was studied using the modified version of the Melli transform for 4.3 level MHV graviton amplitudes in Einstein gravity in a previous paper with Shamik Banerjee and with Ricardo Gonzo. So one of the main results in that paper was the following. So what we did is that we extracted we tried to extract the celestial OP by taking two operators in the 4-point amplitude close to each other, and then expanding the 4-point function in an OP limit and then systematically trying to extract and then systematically try to extract the various terms in the OP limit. So from there, what we explicitly saw was the following: is that the OP has this following structure. So at leading order, it has the following structure where I have this where I have this structure which is Z bar 1,2 by Z12 times some function which is basically the OP coefficient, which is basically the leading OP coefficient, and times another graviton primary operator which has dimension delta 1 plus delta 2 minus 1, and it is being acted on by the super translation mode which is P minus 1 minus 1. Okay. So in this case, that is basically the structure of the leading OP. Now one can compute the subleading corrections as well. And what we found is, interestingly, is that at subleading orders, the singular super translations also arise. So for example, we see that this object P minus 2 minus 1 arises, and this P minus 2 minus 1 basically corresponds to the singular super translations because the vector fields corresponding to this will have poles on the celestial sphere. So in that case, this was the structure. We had P minus 2 minus 1 and also L-1, P-1 acting on the graviton primary operator, which is denoted by G plus and with dimension delta 1 plus delta 2 minus 1. And in this case, there are further subleading corrections, but for the moment, I will not talk about those. So now let's actually look at the structure of this OP. Okay. Okay. So let us try to do the following. So we take this OP and we take a subleading soft limit of this. Okay. So I will take the subleading soft limit of the first graviton here, which is denoted by G plus delta 1. And taking the subleading soft limit amounts to taking the conformal dimension of this to 0. So I'm taking delta 1 to 0, or in terms of the lambdas, I'm taking I lambda 1 to minus 1, because remember that delta 1 is just 1 plus I lambda 1. And so if we do that, then we get something like this, which is denoted in the last equation here. This is just simple to work out from the previous set of equations. So now the point of doing this is the following, is that, so now the point of doing it is the following. So a while back, remember that we computed what the general OP between a subleading soft graviton operator and the generic and an arbitrary matter conformal primary should be. Okay, so if you remember that discussion, then from that, what we should get in the subleading soft limit is that the OP should actually take this form, where now you see that this particular mode of the current algebra, which is denoted by J0 minus 1. So in this case, this should appear. So now if this earlier result of ours is actually correct, then what we should have is that this result, which is in the boxed equation, or it's or the one which I get after taking the soft limit, should actually agree with the first equation in this slide. Okay, so what that means is that we have the following combination. We should then write L minus 1 P minus 1 plus 2J0 minus 1, and then fact some delta 2 times P minus 2 minus 1 acting on this conformal primary operator, which is basically this graviton. So we should set this combination of descendants to 0, right? And so this is just coming from requiring consistency of the OP with the subleading soft theorem. Okay. So I can actually, for convenience, I can write this relation in a slightly different way by shifting the dimension delta 2 to delta 2 plus 1. And in that case, I can just rewrite this equation in a slightly different way, which is given by this. And now I use the fact that so now I can insert this equation, which is an operator relation. I can insert this equation into within some amplitude, right? So in particular, I can insert this equation or this operator inside a correlator which has, let's say, 3 other graviton insertions. So in this case, let me take an MHV configuration, because we started with an 4-point amplitude which was MHV. So therefore, let me take a configuration where I insert this operator inside a 3-point function, where the remaining operators are in the following form, where G delta 2 has in this case positive helicity, delta 3 has minus helicity, and delta 4 also has minus helicity. And then if I use the fact that the correlation function with descendants can be again written in terms of correlation functions of the primaries, with the replacement that there are some differential operators which act on the correlation function of the primaries, then I get the following differential equation which acts on the 3-point MHV amplitude. Okay. So from this, what we have found is that we have found the first order linear partial differential equation which must be satisfied by the 3-point MHV amplitude. And in fact, this can be independently checked by explicitly computing the 3-point amplitude and just acting with this differential operator on the 3-point amplitude, and one can check that it is actually annihilated. So now let me come to let me make a few remarks on some limitations which this analysis has, and this will tie into a question which I guess probably Utin asked actually some time back. So what we will find, so it turns out that the action of some of the current algebra and super translation generators that we talked about in the first half of this talk. So some of these generators actually trivially annihilate the 3-point function. So for example, if you take super translation modes which are given, which are of this form, p minus a comma 0 with a greater than equal to 2, and j1 minus n with n greater than equal to 1, then these actually trivially annihilate the 3-point amplitude, because if you compute the 3-point amplitude, you will find, or the 3-point MHV amplitude, you will find that its dependence on the anti-holomorphic coordinates, or the z bars, is actually through these delta functions. And it is because of these delta functions that these generators will actually trivially annihilate the 3-point function. Now, these delta functions originally are basically a consequence of actually energy momentum conservation, which can be easily argued for. And so this is a certain limitation of the 3-point function. We don't see the non-trivial action of all the generators if we just consider the 4 graviton to 3 graviton OPE case. Right. So therefore, here's an invitation to go to higher points. And for the purpose of this talk, what I will do is that I will consider the case of the 6-point graviton amplitude. Okay. So for discussing higher point amplitudes, we need to write down first the higher point amplitudes. Now there are several people in the amplitudes community. It is very well known that there are several ways of writing writing in point tree level graviton amplitudes. For example, we can use the KLT relations and write it in terms of gauge theory amplitudes. But for our purposes, the most useful representation will be the one due to Hodges, and in this representation, the n-point MHV tree-level graviton amplitude actually takes a very simple form, which in this case is given by this equation. So let me explain the notation of it. So in this case, you see that there is a determinant of a certain matrix. This matrix is an n-3 cross n-3 matrix, which is obtained by removing a set of rows I, j, k, and a set of columns p, q, r from another matrix, which is an n cross n matrix. And this n cross n matrix phi has the following matrix elements. If I is not equal to j, then this is given by the following ratio of the square and angle brackets. And if I is equal to j, then it is given by this combination. So just to mention is that this x and y's which appeared, which actually appear here, are actually some reference spinors, which can be chosen arbitrarily according to convenience, and a particular choice of those reference spinors just corresponds to a particular choice of gauge, and that can be done accordingly depending on the choice one has. Okay, so now I should mention that.
Right.
Yes.
Yeah. Why are you choosing a 6-point? It seems like not 5-point. Or, is there a reason for that?
Yeah. So actually, one can also do. So the 5-point case also one can actually do, and we have actually done that. But this also ties to another remark which Utin was making. So in the case, so let's say you try to do the 5-point to 4-point OP, right? Then as Utin pointed out, is that the 4-point amplitude has this delta function which enforces the cross ratios to be real, right? So if you denote the cross ratios to be z and z bar, then the delta function enforces the cross ratios to be real in the 4-point function. So in that sense, the 4-point function also has some kinematic constraints. So yeah, but if you go to one higher point, let's say if you start from the 6-point amplitude and then take the OP to go to the 5-point amplitude, then the 5-point amplitude no longer has such kinematic constraints, and it is much more general. So it is for this reason that we start from the 6-point amplitude and derive and extract the OP from there. But in this case, as you said, is that actually one can do the analysis completely also for the 5 to 4-point case, and we would get analogous results there. Yeah. So in this case, like, does that answer your question?
Yes. Thank you.
Okay. Thanks. Okay. So let me mention a few points about why we are using this Hodges representation. So one thing is that it is very compact. It is very compact and it is very easy to work with, especially for higher point amplitudes. And also it has some other nice features in this, which is that it makes manifest the SN permutation symmetry of the amplitude. It makes it completely manifest, and it also manifests the Weinberg soft limits. So in that sense, it is actually a very nice representation, at least for our purposes. Okay, so now let me tell you what the 6-point amplitude actually is in this representation. So let me make a convenient choice. So as I said before, that in order to construct the amplitude, we have to take this n cross n matrix and compute its determinant by removing 3 sets of rows and columns. So now for the 6-point amplitude, this phi is of course a 6 cross 6 matrix, and we need to remove 3 sets of rows and columns from it. So let me choose. So this is just a choice. One could make other choices, but this is a convenient one. So let me choose. So let me choose rows 1, 2, and 3, and columns 4, 5, and 6, which are to be removed from this 6 cross 6 matrix. Consequently, I get a 3 cross 3 matrix whose determinant determinant can be computed very easily, and the amplitude takes this following form in terms of the spinor helicity brackets. And then what we in order to construct the celestial amplitude, it is useful to transform from the spinor helicity variables to this omega zz bar variables. And in order to do that, we note that the spinor helicity brackets are given in terms of the omega in terms of the omega i's and the z i's in a very simple form as shown here. And if you substitute this expression for the spinor helicity brackets into the amplitude expression of the amplitude above, then you get an explicit answer for the 6-point amplitude, which takes this form. It has a slightly complicated dependence on the z and z bars, but that is what it is. Okay, so now in order to study the OP, we want to relate the 6-point amplitude to a lower point amplitude, because we want to show that the amplitude factorizes in the OP limit. So for that, it will be important for us to actually know what the 5-point amplitude also is. So the 5-point amplitude can also be computed. So we can write down the 5-point amplitude also using Hodges formula, and in this case it takes the following form once we write it in terms of omega and the zz bar variables. Okay, so now let's do the Mellin transform. So here we are doing the modified Mellin transform as I said before, with this exponential factors inserted in. So now in order to do this integral, we first notice that that the momentum conservation imposing delta function, which is this delta of 4, that can be represented in a particular way, which is shown here. So what you can do is that you can use the constraints of energy momentum conservation and solve for and fix you can fix 4 of the energy variables out of 6 in terms of the remaining 2. Okay, and here I have done a particular change of variables where I have taken two of the energies, let's say omega 5 and omega 6. I performed a particular change of variables. I have written it as omega p times t and omega p times 1 minus t. It's just a convenient change of variables. And if we do that, then the momentum conserving delta function can be represented in this way, where you see that now 4 of the energies for 4 of the omega i's are completely fixed, which are denoted by omega I stars, and these omega I stars have some very explicit form in terms of this variable omega p t, and then this parameter t, and also the other coordinates, which are the remaining z and z bars. So in this equation, I have not explicitly written this, but this sigma ij's are some known explicit functions of zij and zij bars. Okay, so we should, and these can be actually very easily computed, but their expressions are a bit lengthy, so I have not included them here. So in this case, notice one thing, that I have written it in a form where I have explicitly written these factors of z56, z bar 56, etc. in here, and this I have done because what I want to do is that I want to consider in this 6-point amplitude the OP between gravitons 5 and 6. Okay, so in this case you could consider, of course, the OP between any 2 operators, but in my case I will concentrate on the OP of gravitons which are labeled by 5 and 6. And so this is a convenient parametrization. Okay, so now one can go ahead and compute okay. So now we note that so we had this delta function.
What is the
where 4 of the
in this?
Yes.
What is R in your denominator?
Oh yeah. So yeah. So basically R here is the cross ratio. So R is R1 to 3,4 is Z1 to Z34 by Z1 3 Z24. And R bar is the Comptes conjugate. Right, okay, so now we substitute this representation of the delta function in the Melli integral, and because of the particular representation of the delta function, we already see that 4 of the energy integrals are localized, and we don't have to do any, and we don't have to do 4 of these integrals anyway, because the delta function just fixes them. We are left with now with an integral over this parameters omega p and t. So these are the only 2 integrations which we have now to do in order to completely determine the Melli amplitude. So now if we do the integral over this parameter omega p, then we get an expression which looks like this. It is a somewhat complicated looking expression. The integrand is an explicit function again of these variables sigma i's. It's and z56, z bar 56, and so on. Okay, and there are some prefactors which also have some explicit form. Okay, so one thing I should mention here is that the sigma i comma j's, which appear in the various formulas here, the sigma I comma j's do not depend on z56 and z bar 56. The z56, z bar 56 dependence has been completely factored out, and this will be important when we expand the amplitude in powers of z56 and z bar 56, which would correspond to the OPE expansion. Okay, right. So now let me mention the general strategy for extracting the celestial OP from the amplitude. So in this case, if suppose we want to extract the OP of gravitons 5 and 6, then we just expand the Melli amplitude in powers of z56, z bar 56, and u56. Okay, and we keep all the remaining zij's, z bar i''s, and uij's to be fixed. Now in this previous slide, we see that there are also these theta functions which appear in this Melli integral. These theta functions are appearing because of the fact that the energy variables which we were integrating over in the original integral, so those energy variables are restricted to be positive, right? We were integrating from 0 to infinity. So these theta functions basically enforce that constraint. But when we are trying to extract the OP, we might get some terms which come from taking derivatives of the theta function with respect to z56 or z bar 56. But in the OP limit, we can actually ignore these contributions, because these contributions from the theta functions will be proportional to delta functions, and the arguments of those delta functions will be zij's and z bar ij's, but these zij's and z bar ij's will not involve z56 and z bar 56, and so by definition, in this case, such delta functions will never click, and therefore in the OP expansion, these contributions can be neglected, and so that's what we will do in the rest of this section. Okay, so now let's consider the leading term in the OP. So now we do this. So now we expand in Z56 and Z bar 56. The leading term turns out to be the following. It turns out that there is a leading singular term in Z56, and there is a numerator, which is Z bar 56, and then we are left with an integral of the following form. Now the integral over the t parameter, that just gives me this Euler beta function, which is b of I lambda 5 comma I lambda 6, and then the remaining part is basically the 5-point Melli amplitude, where with the action of this p minus 1 minus 1. Now this p minus 1 minus 1 is nothing but the derivative of the 5-point amplitude with respect to the u6 retarded time coordinate. Okay. And it turns out that this particular combination of this prefactor which we had in the Melli amplitude is actually related to the 5-point Melli amplitude in the following form. Okay, so basically what we get at the end of the day from doing this is that this equation, which is the leading term in the Melli amplitude, therefore can be used to extract the leading OP for two positive helicity gravitons, right? And the leading OP now takes this following form, which is shown in the boxed equation here, and so this is the leading term, and this is the leading term, and the structure of the leading term is of course the same as we got from the 4-point to 3-point case. So now I want to consider the subleading terms in the OP. So now at higher points, we'll have some new contributions which don't happen in the 4 to 3-point case. So for example, there is an order 1 piece, which is of order z to the power z5 to the power 0 and z bar 56 to the power 0. And that term, if you work it out from the amplitude, it turns out that it is basically related. Okay, so sorry, this A5 should actually be M5, the 5-point Melli amplitude. But the point is that the Melli amplitude or the order 1 contribution to the Melli amplitude in the OP limit basically can be written as the action of the supertranslation of the singular supertranslation generator p minus 2 comma 0 acting on the 5-point amplitude, on the 5-point Melli amplitude. Okay. So now what we can do is that we can now try to see if this answer of ours is actually consistent with the subleading soft limit. Okay. So we can take the subleading soft limit here. So let's say we take subleading soft limit on the 5th graviton. So what we should do is that we should multiply this Melli amplitude by 1 plus I lambda 5 and take the limit I lambda 5 goes to minus 1. Okay. So sorry, there are a couple of typos here. So so what I meant by taking in this limit, what I should have is that I should be considering the ordered 1 term here. So sorry, yeah, so this is a typo, but this I will correct in the slides that I submit. Okay, but the essential point is that if you take the subleading conformal soft limit, then at order 1, the term which you should get is basically this current algebra is basically one of these current algebra generators that we saw before, acting on the 5-point Melli amplitude. And so therefore, if we demand that this answer in the second line is consistent with the answer that we get explicitly from the calculation of the amplitude, if these two, so we now have to demand that these two equations are basically the same. Then doing that, then doing that leads to a particular relation of the following form, okay, which is written in this last equation inside this box, which basically again says that a certain that a certain differential operator, which basically corresponds to a given mode of the of one of the current algebra generators acting on the 5-point amplitude, is actually related to a certain supertranslation mode acting on the 5-point amplitude. Okay, okay. So in this case also we see that we have a situation which is analogous to what we found in the 4-point case, where there is a certain combination of descendants which when acting on the lower point amplitude, they basically annihilate it. Okay. So now one can go ahead and compute other subleading orders. So for example, there is an order Z56 term, which now involves the supertranslation mode p minus 3, 0 and L minus 1 p minus 2, 0. L minus 1 is basically the derivative with respect to Z6, and once again demanding invariance or demanding that this answer agrees with the general result from the subleading conformal soft limit, will tell us that the following combination of descendants written in this boxed equation, so that also acting on the 5-point function actually annihilates the 5-point function. Okay, and using this relation, one could rewrite the OP in this form as well. So now one can play the similar game at other orders. For example, there is an order Z bar 5-6 term, which can be expressed in this way, and here and actually here we see the difference with the 4 to 3 point case, because in the 4 to 3 point case, what happened is that this generator, which was this L bar minus 1 p minus 2, 0, so that did not appear because p minus 2, 0 trivially annihilated the 3-point amplitude. But in this case, we find that we do find a non-trivial action of this supertranslation generator, and once again demanding equality with the general result from subleading conformal soft limit, again tells us that there is a certain combination of descendants which acting on the 5-point amplitude annihilate the 5-point amplitude. And then, okay, so just to advertise, there we can go to even higher orders and write the Z56, Z bar 5-6 term, which takes this form. Right. So now the important point in all of this discussion. If you lost track in all of this expressions, but the takeaway point from this is basically the following: is that from the explicit computation of the amplitude, at least to this order, to the order under consideration, Z56, Z bar 5-6, we have been able to write every term in the OP limit as some differential operator acting on the lower point amplitude, and these differential operators are nothing but the representations of actually this current of the current algebra generators and supertranslations. So yeah, so actually this actually tells us that at least from the amplitude we have strong evidence that this factorization in the OP limit works, and things really can be expanded, and the OP can be organized in terms of representations of the current algebra and supertranslations. So in this case, that should be the takeaway point from this set of slides. Okay, so that brings me to actually the last part of my talk. So actually I should ask, so actually how much time do I have, Alok?
I mean, how much time do you need? Can you just roughly?
Well, I think I can complete within, let's say, in another 15 minutes.
Sure, go ahead, please.
Is that fine? Okay,
yeah.
Okay. And also let me actually stop to see if there are questions at this point. Okay, fine. So if there are no further questions, then let me proceed. So in the last part of my talk, what I'm going to do is is that basically I'm going to now turn to a completely symmetry-based analysis, and I will show that there is a completely symmetry-based way of deriving these OP coefficients and the role, and in this case, the crucial role will again be played by this extended symmetry algebra, which is this combination of the SL2C bar current algebra and supertranslations. Okay, and we'll also see that the answers that we get from the explicit from the symmetry-based analysis will precisely match with the explicit computations which we can do from the amplitudes.
Sudip, sorry, maybe can I ask?
Yes.
So for the MHV amplitudes, there is this.
Yeah.
Actually, this also came up yesterday in one of discussion. There is something called soft exactness. So you can always write the endpoint MHV in terms of n-1 and just stripping off gravitational soft factors, Weinberg soft factors.
Right.
So from that perspective, like you would not even need a OPE to get this result, right? I mean, it should be even valid away from the collinear limit for MHV amplitudes. I mean, so maybe for MHV we have a convergent expansion, which in fact stops at this order that you are considering, right? Because these are exact, soft theorems are like basically exact statements for MHV. They are not like, they are not, there are no other terms, higher order in the frequency. I mean, from that perspective.
Yeah, but let me ask you this. So in that, but in this case, is that true also for higher point amplitudes?
Yeah, for any point, for any point amplitude, I think that the McGardy's proof was, I mean, the McGardy's statement is for any point, right? Maybe I'm mistaken that endpoint can be written as stripping of soft factors, and maybe the decomposition is complicated. There are some permutations involved in all. The formula is not as compact as Hodge's formula, but I thought the formula is valid for tree-level amplitude generically. Inverse of
So I may be wrong about this. So actually, somebody should correct me if I'm wrong.
No, actually, Shamik is saying it's only up to 6 point, but I think so that maybe
So basically,
I think Song is not here. Otherwise, he would have said clarified this. That I thought it was for any point endpoint.
Yeah, so basically I remembered from actually the Strominger-Cachazo paper where they actually first showed some of this using MHV amplitudes. There I remembered the statement was that it holds only up to.
There was a paper by McGardy which came out that he showed that it is an exact construction. It's called inverse of construction for MHV amplitudes. I don't know if Savan is. I don't know if he said, maybe he can clarify, or anyone else who knows maybe.
Yeah, I'm not sure. I didn't know if this was true for both. Like I didn't know it was true for gravity as well. Like I thought it was mostly for Yang-Mills, but
no, it is true for it is true for gravity. That I'm fairly positive, but I don't know if there is a limit on the number of particles. Which is inverse of construction. Yeah, but maybe we can discuss later.
Yeah,
sure. Okay.
So up to 6 points you are saying, but it's true. The soft exact statement is true anyway. Up to 6 point MHV. I mean that you agree. So that I thought that's what you were saying, right? That up to some point it is true that.
Yeah, right.
But since you are looking at 6 point means that your expansion is really convergent in some way, right? You didn't have to do OP then because you are also looking at 6 point. So maybe it could be like, I'm just saying that your expansion could be more like for MHV, it could even be like more powerful than
so that is true in some sense. So in this case, I showed this for order Z56, Z bar 56, but actually one can actually go to even higher orders systematically by just reading off different powers of Z56 and Z bar 56. So in this case, we are basically taking some sort of a holomorphic collinear limit. You treat Z and Z bar as independent and take Z56 to 0 and Z bar 56 to 0 independently, and you just read off the powers of their and just read off their powers from the MHV amplitude, from the 6 point MHV amplitude, and that can be done to higher orders as well. And the structure which I have shown up to the Z56, Z bar 56, so that presumably extends to other higher orders as well. Okay, good. Okay, so thank you for the questions. Okay, so now let me turn to this symmetry analysis. So now so now from the previous amplitude computations, what we essentially, one of the important lessons that we learned is the following: is that we saw that certain linear combination of descendants, which when acting on MHV amplitudes, so those annihilated the MHV amplitude. Okay. Now it turns out that such combinations of descendants must actually be primary operators themselves under the extended symmetry algebra. And now this situation where we have that some linear combination of descendants, they vanish acting on primaries. So that is a situation which is actually very analogous to the case of null state relations in 2D CFTs. But I will actually refrain from using that specific terminology because null state relations in ordinary 2D CFTs are often related to unitarity and so on. Yeah, so in this case, I will refrain from using that specific language. But this is something useful to keep in mind, that these vanishing conditions, that certain combination of descendants annihilate the 5-point amplitude is actually, or general Melli MH is actually very similar to what one sees in the case of null state relations for 2D CFTs. So now the point is that we can actually determine. So we saw that there are these vanishing state conditions from explicit computations of the amplitude, but we can actually determine this what combination of descendants what combination of descendants will vanish. So we can actually determine that completely from symmetry considerations. So in this case, let me actually show some examples of this. So say suppose we consider a certain linear combination of states, which is, let's say, this current algebra mode J1 minus 1, P minus 1 minus 1, plus the super translation mode P minus 2, 0, with some arbitrary coefficient C acting on some graviton primary operator, where the sigma denotes the spin here. Okay, so the sigma is right. So in this case, sigma can either be plus or minus 2. Now, what one can show is that both of these states in this linear combination are actually individually primary operators under the Poincare group. Okay, but now what we will do is that we will demand that this linear combination is also a primary under the full extended under also the current algebra. Under also the current algebra. And what this means is that we should impose the following condition, that the modes JAN acting on the primary state psi sigma should annihilate it for n greater than equal to 1. So in particular, if we, for example, apply if we apply this particular mode J minus 1 of 1, if we act with this on the state and demand that it is 0, then we can show from that it uniquely fixes this coefficient C, and this is given by 2h bar plus 1. Okay, and this coefficient actually precisely agrees with what we found from the order 1 term in the calculation of the 6-point MHV amplitude. So that can be easily checked, and moreover, it can also be easily verified that this particular state is also annihilated by this set of super translation modes. And so therefore, what we learn from this completely symmetry based analysis is that if you give me this state, which is a linear combination of these two particular states, then the psi sigma is a primary descendant of the extended symmetry algebra. Okay. So now, So now, in exactly the same fashion, we can construct other states which also become primary descendants, or in a usual standard in a standard unitary 2D CFT, you would call such states to be null states. So for this, let us consider this particular linear combination, where phi is a linear combination of actually four actually four such generators. Right. So we have L minus 1, P minus 1, J1, 0, P minus 1, P minus 3, and L bar minus 1, P minus 2, 0. Okay. So if we act on this, so if we demand that this is a primary under the Poincare group, then we should impose the following conditions: that it is annihilated by L1, L bar 1, P0 minus 1, and P minus 1, 0. Okay. So if we do that, then that fixes uniquely the coefficients C1, C2, and C3 to take the following values. And one can also see from that, and one can also see from there that and one can also see from this is that this set of conditions are also satisfied only when the helicity or the spin of this graviton primary is equal to +2. Okay. So now one can check that given this set of coefficients, this state capital phi is also a primary under the extended symmetry algebra, in the sense that it is annihilated by the following set of modes: Jan with n greater than 0, Pn minus 1 with n greater than equal to 0, and Pn, 0 with n greater than equal to -1. Okay. And so therefore we learn that this linear combination, which is denoted by capital phi, is also a primary descendant of the extended symmetry algebra. So now what we can do is that we can take this vanishing we can take this operator relations which were shown before, and we showed that these are primary descendants in the sense that they are they are annihilated by that they are primaries of the extended symmetry algebra as well. So now what we can do is that we can take these combinations and insert them inside MHV celestial correlators, which correspond to the MHV graviton scattering amplitudes. Okay. And then using the fact that we can write these correlation functions in terms of correlation functions of primaries with the differential operators acting on them, we get the following differential equation. So now I think this is an interesting result, because it says that we have these differential equations which act on arbitrary endpoint MHV scattering amplitudes, right? Or more appropriately, the celestial correlators corresponding to them. So that we can do for the other primary descendant as well, and we get another differential equation which should also be satisfied by MHV graviton scattering amplitudes. So now let me make a few comments on the structure of these differential equations. Okay, so first of all, what is the evidence that these differential equations are satisfied? So first of all, we can actually, so in this case, the first differential equation which appears in this slide, so that can be it can be analytically verified that this actually holds for endpoint MHV graviton amplitudes by using Hodge's representation, and for the second one, it's actually a bit hard to show it directly from explicit amplitude computations, but one can do it analytically for up to 5-point MHV amplitudes, and one can numerically check it at higher points. For example, we have shown that it works. For example, we have numerically checked that it works for n equal to 6 points. Okay, it also, I should also say that these two sets of differential equations are not actually independent, because it can be shown that the second equation can be derived from the first using special conformal transformations. Another point is that in these two differential equations, we see that we have both L minus 1 and we also have L bar minus 1. Now L minus 1 and L bar minus 1 are nothing but derivatives with respect to Z and Z bar, right? So therefore we have both holomorphic as well as anti-holomorphic derivatives in these differential equations, And so what this means is that you cannot factorize these equations in a holomorphic fashion. And that is also a reflection of the fact that the underlying infinite dimensional local symmetry algebra does not admit a holomorphic factorization. And this is also something, and this should also be contrasted with standard 2D CFTs, because in case of standard 2D CFTs also, it is possible to write down similar actual null state relations. For example, in the case of 2D CFTs which have current algebra symmetries, in that case the null state relations or the differential equations are basically known as the Nizhny-Zamolodchikov equations. But in those cases, what one can show is that actually in those cases one can actually holomorphically factorize, but that is not something which we can do here. So now in the rest 5 minutes or so, which I guess I have, I will now show that how one can use these differential equations to completely determine the structure of the leading OPE coefficients, and also comment on what happens for the subleading OPE coefficients, which are the OPE coefficients for the descendants. Okay. So to do that, let me start by writing out the OPE between two graviton operators in the following general form. Okay, so here I have taken, and also I will assume for this discussion that the gravitons which I'm considering, or the operators, the graviton primary operators which I'm considering, they correspond to outgoing gravitons in the S matrix. Okay. So with that, let's write down this. So we have this. So here, what I have done is that I've written the general form of the leading OP between two graviton primary operators. One of them has positive helicity denoted by plus, and the other one can have any helicity, either plus or minus 2. Okay. So now what we do is that we take, let's say, the differential equation which involved this particular combination of modes, that is this particular current algebra mode J1 minus 1 and the supertranslation mode P minus 2, 0. So we saw that there is a certain linear combination of this, which is a primary descendant, and so therefore I can act with it in and therefore that should decouple from MHV scattering amplitudes, as we just discussed. So now let me write that decoupling relation in the following form, as is written in this equation here. So now what we can do is we can adopt the following strategy. So let's take the holomorphic collineal limit here, which means that I take, let's say, z goes to z1. Okay, and so here I have some. So here this script j1 minus 1, script p minus 2, 0. These are some differential operators which will depend on z and z1. So what we can do is that we can expand these differential operators around these points z and z1. So now there will be some singular terms in that expansion. For this discussion, we can just focus on the singular terms. Okay, so because those will be the terms which are the most relevant in the z going to z1 limit. So we do that, and also at the same time we also insert the form of this. We also insert the form of this general OP inside this correlation function, and then we try to match the powers of z minus z1 and z bar minus z1 bar from both sides. Okay. So then trying to do that matching basically leads us to following an equation of the following type, which is this first equation on this slide. So notice that this equation is now an equation for the leading OP coefficient, which was denoted by C P subscript P comma Q. Okay, so this equation we are getting from the application of one of the differential equations that I mentioned, but we have also another differential equation. So we can take that differential equation, do this expansion in the holomorphic collineal limit, and insert the general form of the OP, and then again match powers of Z and Z bar from both sides and see what we get. So doing that analysis basically leads us to another equation for the leading OP coefficients, which is given by the second equation here. Okay. Now one can show is that these equations will have non-trivial solutions only if these exponents P and Q, which appear as these numbers P and Q, which appear as exponents of Z and Z bar in the general form of the OPE, are given by Q equal to 1 and P equal to -1. Okay, so one can show that this is the only non-trivial solution of these two sets of equations. Okay, so then what we get from there is that the leading. Okay, so now we can just insert this result Q equal to 1, P equal to -1 back in this general form of the OP, and from there we see that the leading structure of the OP should actually take the following form, which is Z bar minus Z bar 1 by Z minus Z1 times the leading OP coefficient and the other primary operator. Okay, so now this factor of Z bar minus Z bar 1 by Z minus Z1, which is coming here. So that structure is precisely the structure which you would get which one gets if one considers a two-derivative theory of gravity, because essentially this structure is basically coming from the structure of the three-point vortex in Einstein gravity, and if you explicitly look at the three-point vortex in Einstein gravity, then go to this conformal basis, do the Melli transform and so on, then you will find that in the holomorphic collinear limit, the structure of or the leading structure is basically given by this particular form. So therefore, what this analysis is actually telling us is that the bulk gravitational theory that is probably dual to the MHV sector of the celestial CFT must be a two-derivative theory of gravity, because from the symmetry analysis we just showed that the structure which we get, it precisely corresponds to a two-derivative theory of gravity. Okay, so we can actually go ahead and also compute the. Okay, so we fixed the form of the leading OP coefficient in the sense that we fixed what are the exponents of Z and Z bar that appear in the leading OP from these differential equations. We can do more. We can actually also compute the leading OP coefficients as well. So we take one of those. Recursion relations which we got from applying those differential equations for the leading for the OP coefficient, and then we conjugate this with another set of recursion relations which comes from demanding that the OP is invariant under the global space-time translations. Okay, so that gives us the second equation here, and now one can check that these two sets of equations are uniquely solved if I take this OP coefficients to be given by this Euler beta functions. Now there can be a coefficient alpha which is a priori arbitrary, but that coefficient can actually be fixed by taking into account the soft limits. For example, the leading conformal soft limit can be used to fix alpha, and it turns out that alpha gets fixed to -1. So what we see from this analysis is that we now have, from a completely symmetry-based analysis, we have entirely fixed the structure of the leading OP as well as the leading OP coefficient. Now this can be the same thing can be actually repeated for the case where the gravitons that we considered here were not both outgoing. One of them could be incoming, the other could be outgoing, and vice versa. So that can also be dealt with in exactly the same fashion, and the structure of the leading OP and the OP coefficients can also be determined exactly from the symmetry-based analysis from there. Okay, so now let me, okay, so now towards the end, let me make a few comments on what about the OP coefficients for the descendants, right? Okay. So for now, so for that, what one can do is that one can. Okay. So now the point is that we have reasonably good confidence in the fact that the OPE can actually be organized in terms of representations of the SL2C current algebra and super translations, because we have all this, because we have explicit checks from the amplitude. We have the symmetry-based analysis checks, which also determine the leading, which determine the structure of the leading OP coefficients. So we have we have some reasonable degree of confidence in this, and therefore what we can do is that in order to write down the structure of the subleading terms in the OP expansion, we can so what we can do is that we can just write down all possible terms which are allowed by the current which are allowed by the symmetries of the theory, which are in this case which are allowed by this extended symmetry algebra. And then what we do is that we demand, and so that I have written in this equation here up to a particular order. One can write this at higher orders, but then that would fill up the entire slide. So I have written it only up to a few orders. But then the crucial point is that we now demand that both sides of this equation transform in the same way under the extended local symmetry algebra. So demanding that will give us will lead to certain recursion relations for this descendant OP coefficients denoted by this alpha i's. We also should take into account the vanishing conditions or the null state relations that I mentioned before, and combining all those together, one can show that these recursion relations can actually be solved, and the OP lead and all the descendant OP coefficients, these alpha i's, they can be determined in terms of the OP coefficient of the leading primary operator and the leading OP coefficient in this case being given by this Euler beta function. And up to the order that I have shown here, we have actually checked that the solutions to these recursion relations they actually precisely match with the corresponding results that you get by explicitly computing by explicitly doing this amplitude computations. Like for example, the results which I showed where I expanded the 6-point MHV amplitude and OP expansion and obtained various terms in the subleading orders in the OP expansion. So the coefficients that you get from that explicit amplitude computation also precisely agrees with the solutions of these recursion relations. Okay, so in this case, all of that is strong evidence in favor of the fact that for MHV amplitudes, the OP indeed is organized in terms of representations of this current algebra plus super translations. Okay, so now I'm almost done, and so let me conclude. So what we have done in this talk is that, or what I have shown is that I have showed that there is a certain current algebra which can be constructed from the subleading soft graviton theorem for a positive helicity outgoing graviton. So that is what I did in this particular talk. One could generalize this to the case of the negative helicity graviton as well. And then the important point was that for tree-level MHV amplitudes, the celestial OPE of positive helicity gravitons, I argued that it can be organized into representations of an extended symmetry algebra, which comprised of the SL2C current algebra and super translations. And one of the important players in this game was actually this null state these relations which were analogous to null state relations, which we are familiar with from ordinary 2D CFTs. And these null state like relations lead to partial differential equations for the celestial correlators corresponding to MHV graviton amplitudes. And actually I should say that it will be interesting to see whether one can actually solve these differential equations explicitly one would need to implement the appropriate boundary conditions in this case, but it will be interesting to see whether one can actually use those differential equations to actually completely solve for the MHV amplitudes. But then the point is that all this discussion sort of implies the following statement, that the celestial CFT which computes these MHV graviton amplitudes can be thought of as a certain decoupled sector which is entirely governed by this SL2C bar current algebra and supertranslations. So just at the very end, let me mention some future directions. So it would be interesting to now understand the structure of celestial CFT correlators for NMHV graviton amplitudes, which are much more complicated than MHV graviton amplitudes, and in that case, it is most likely that the current algebras for both the positive helicity as well as the negative helicities of gravitons will play an important role, and they might also start actually talking to each other instead of just being decoupled as in the MHV sector. It will also be interesting to investigate whether there exist similar structures in the case of other amplitudes, let's say like Einstein-Yang-Mills amplitudes. And one thing to explore would be to what lessons, if any, can we learn about, let's say, double copy-like structures for celestial correlators from this analysis. So with that, I will end, and actually thank you very much in this case for your attention.
More questions. There were a lot of questions, of course, during the talk, but yeah. So, Sudip, have you thought about this last point a bit? Like, because this for MHV, there is a nice way to do the double copy, right, of the gluon amplitude.
Right.
Have you looked at?
So I have not very carefully thought about this, but there was also this recent paper by Stephen Steiberger and collaborators where they explored some double copy-like structures. For example, they construct they construct a Sugawara type stress tensor.
Yes, right. But that was Einstein-Yang-Mills, no? Wasn't it Einstein-Yang-Mills, or was it pure MHV?
Right. So that was Einstein-Yang-Mills, I think.
But just for pure, I don't know if they looked at like from pure gluon to pure gravity double copy, which is there for MHV nice.
So that will actually be interesting to actually try to understand. But I don't have anything sharp to say about it at this point.
Any further questions? Okay, if not, let's unmute, and thanks, Sudip, for a fantastic talk.